John here. He's also former Harry Potter at some point, right? And he'll talk about applications of homotopy algebras from color kinematics realities.
Well, thank you, Elizabeth and Christian, for setting up this wonderful conference and inviting me, giving me a chance to talk. Really nice being back in Edinburgh. It's one of my favorite places. I'm going to talk about applications of homotopy algebras, and Martin and Urs did a great job introducing homotopy algebras. So I spent the lunch break deleting all my slides introducing homotopy algebras, which is good. We'll get a little further into the discussion. I'm very much the and physics part of this conference, but I'll try to reach across the aisle and motivate mathematicians to be interested in what I'm doing. Inevitably, I'm going to find that sweet spot where the mathematics is going to be really naive and the physics is going to be inscrutable. So, no one will understand anything is what I'm trying to say. And this is work done with lots of collaborators. Many of them are here today. We heard from Martin earlier. Christian's one of the organizers. I wanted to highlight Simon Jonsson because he's a former PhD student at Hertfordshire. He's currently applying for postdocs. He did lots of good work with me on that. And my current PhD student, Dimitri Kalafas, who will be applying in the nearest future. So I would normally, be talking to dyed-in-the-wool particle physicists that are drunk the homotopy algebra Kool-Aid. I want to try and motivate what we're doing. And one of the ways I do this is to say that actually physicists have just been doing homotopy algebras their whole lives. Secretly, they've been doing this forever. And the key idea is this very elementary concept of resolutions, which I think we can kind of trace back to, at least formally, to the beginnings of homological algebra and Hilbert's syzygies, where you want to encode the relations amongst linear bases of solutions and the relations amongst those relations and pack them all up into this nice resolution. And then we quickly realize that we should identify all objects of interest with an object of interest with all of its resolutions. And then this isn't quite sufficient. We find non-trivial cohomology popping up in non-zero degrees, and we generalize this to arbitrary complexes up to quasi-isomorphisms. Other textbooks are available, but Manon will be a hero of my story later, so I may as well flash his up as opposed to anyone else's. And then finally, we might be interested in compatible algebraic structures. And in this process, we realize that these compatible algebraic structures have to be relaxed up to homotopy. And this is kind of the starting point here. You should think of these as being particle interactions in the kind of way that Martin described. So what would I say? Why have physicists always been doing this? Why have they always been doing these resolutions in this kind of sense? Well, because what does a physicist do? They measure things. They get a bunch of numbers that encode, say, the probabilities of some particles to go in and some particles to come out. And these numbers display lots of patterns. They're constrained by many things, but they're just a bunch of numbers. And we realize that these patterns, and we find this web of relations and constraints, and these would be due to space-time symmetries, conserved charges, spin statistics, the equations of motion, all sorts of things. And we want to make those properties of these sets of numbers apparent, and do that via resolutions. And I suppose the most relevant form of this is through the BV formalism, where we might have some classical field theory that satisfies some equations of motion and has some gauge symmetries. And to manifest those things, make them nice and simple, the kind of constraints introduced by those gauge symmetries and equations of motion, we enlarge the space of fields to include ghost fields. This is typically called the BRST complex. And we further enlarge the space to include something we call anti-fields, which encode the equations of motion. And there's a whole formalism associated to this, which I will not go into. Okay, so what am I going to do for the rest of the talk? I'm going to begin with a very brief review of homotopy algebras and quantum field theory, leaning heavily on Martin's talk before lunch. And then I'm going to dive into some applications. So I'm going to start by talking about what's known as color kinematics duality. This is a particular property of certain quantum field theories, and we want to understand this property in terms of homotopy algebras. Then I'm going to talk on going on to talk about more generalized observables. So this color kinematics duality is associated to scattering amplitudes, the things that experimentalists measure at particle accelerators. But these are not the only things one could measure. I'm going to go on to some generalized amplitudes and think about this from the same point of view. And then finally, I'm going to end on holography. And if we have time, I'll get on to what are called AKSZ-Manin theories for gauge theory and gravity, and make a little contact with generalized symmetries in this context. Okay. So this is my very naive introduction to homotopy algebras. Let's consider a cochain complex with some compatible multiplication map. It's an algebra. It's got compatible in the sense that the differential is a derivation. You could ask the question, oh, here's an example, the one example to have in mind, P forms with the exterior derivative. And in fact, this is graded commutative because the wedge product is graded commutative. That's the key form for most physics applications to have in mind, or at least the ones I'm going to discuss. And then you could consider morphisms between these differential, these cochain complexes. And you could ask, can the algebraic structure on the first be transferred to an algebraic structure on the second? And if you want to be really strict about it, the answer is no. Generically, this doesn't work. But the answer is yes if you allow for a richer homotopy algebraic structure. The idea is that the basic algebraic identities will only hold up to homotopies. And these homotopies are characterized by higher products. These are these higher brackets that Martin and Urs were talking about. So in addition to the differential, the algebraic product, the binary bracket will get ternary brackets and so on, all the way up. It may terminate at some point. It may not. So informally, you should just think of homotopy algebras as familiar algebras where you include higher products and higher relations that encode the kind of key identities of those algebras up to homotopy. So associative algebras become homotopy associative, commutative algebras become homotopy commutative, and Lie algebras become homotopy Lie algebras. And it's going to be the commutative, the C infinity, and the L infinity algebras are going to be the stars of this story. So that's all I'm going to say, but I want to remind you about a few things that Martin already mentioned that are the key things to keep in mind for my discussion. First of all is this strictification or rectification theorem, which says that every L infinity algebra is quasi-isomorphic to an L infinity algebra that only has non-trivial binary and unary bracket. There's this minimal model theorem that says that every L infinity algebra is quasi-isomorphic to a minimal L infinity algebra, where the underlying graded vector space is just the cohomology of the original one, and obviously the differential vanishes. And in practice, we will use this technology of homotopy transfer to go from one kind of L infinity algebra to another. I'm going to come back to this, but let me just flash it up here. I'll come to describe in a little more detail what's going on in these equations from the physicist's point of view. There's a really natural interpretation of what's happening here. Okay, so this is a claim that Martin basically explained to you. Every perturbative Batman-Vilkovitsky field theory is given by some cyclic L infinity algebra. And I've deleted all my slides explaining that because you just had an explanation earlier. But just to remind you of how this dictionary works. So because I'm considering just perturbative quantum field theory, I'm rarely thinking about BV manifolds over a point, and they correspond to cyclic L infinity algebras. Cyclic being meaning that there is this inner product here. So the brackets correspond to the BV differential or the degree 1 homological vector field on the BV manifold. The graded vector space of the L infinity algebra corresponds to this space that I introduced in the first slide. This is the field content of your theory coupled with the ghosts. And then you take this degree shifted cotangent bundle, and that gives you the anti-field. So you get this space of ghosts corresponding to gauge transformations fields corresponding to the fields, anti-fields corresponding to the equations of motion, and then anti-field ghosts corresponding to Noether identities. We have the cyclic structure here related to the symplectic form on the BV manifold. And then we have this homotopy Maurur-Cartan action, which is constructed from the brackets, and the cyclic structure corresponds to the classical BV action. So that's my lightning summary of how these two things are related to each other. But if you have any questions, I don't have to go quite so fast. Martin described homotopy Maurur-Cartan actions. I just wanted to flash these formulas up again, mostly to say, here is the homotopy Maurur-Cartan action for an L-infinity algebra. We take the sum over all brackets with some degree 1 element inserted, and then we dot it in using the cyclic structure in this way. I just wanted to remind you of that form. Okay. This was all classical, so everything here was just classical physics. There's no quantization, and following Martin's hint, I thought I'd add one slide on quantum L-infinity algebras. So I do have something to say now. So all of this gets generalized to a quantum L-infinity algebra, which the slickest way of saying what it is, it's a co-derivation on this free symmetric tensor product algebra of where you have this formal power series in H bar, such that you get this identity here, where this is the BV Laplacian and this is the co-differential. Unpacking that a little, what it means is that you add in for every bracket, you've got a genus G family of these. So G runs over all integers, all positive integers, and it counts the number of loops in your quantum expansion. Actually, I see that Brano's here. Welcome. And you can ask him for the full details of this. He's an expert. And you can, just as Martin was describing, where a classical Maurur-Cartan elements, you can define quantum Maurur-Cartan elements. And they are like a genus G expansion of classical Maurur-Cartan elements. Okay, so you should think of this, think of the new brackets that are appearing here as corresponding to how many loops you have running in your Feynman diagrams, if you're familiar with that language. Now you can do something nice to this. You can take, you can add what we call sources to the original quantum L-infinity algebra through its Weil algebra. And then once you've done that, you can take a Legendre transform to what in the physical terminology would be called the 1PI action. And this is like an effective action that encodes, it looks like a classical action, but it includes higher order corrections that capture all of the quantum mechanical nature of the system. And then this is effectively just a classical L-infinity algebra now, and you can take its classical minimal model. Now we're just doing standard L-infinity algebra techniques. And we're essentially passing from a quantum L-infinity algebra to a classical effective action over this formal parameter H bar. And that kind of connects, if you're familiar with Costello and Williams' work on, or perspective on the BV formalism. Okay. And just as classical Maurur-Cartan elements were in the critical locus of the classical homotopy Maurur-Cartan action, these quantum Maurur-Cartan elements make stationary the effective classical action that we generate from this process.
Great. So in the previous slide, the previous one, I think so you relate the BV action with this Maurur-Cartan theory. So in my mind, Maurur-Cartan theories are either like Chern-Simons or higher versions of Chern-Simons theory, right? Mm-hmm. And the claim is that any gauge theory can be written as equivalent to, that is a claim?
That's the claim.
But for example, how do two, like, okay.
So it would actually be helpful if I hadn't cut the example. I could have showed you, but it was rather that up. So so let's say you might say, well, Yang-Mills, you understand for Chern-Simons. I think you can see how this would work for Chern-Simons, right? So Yang-Mills doesn't come in this form. if you integrate, so you have to take the derivative off the first A and put it on the second, so you can integrate by parts. So this actually breaks down if your manifold has boundary. You have to say a few more words, but I'll say those words at the end. So you can integrate by parts to put the derivative that would be on this side. So you normally you'd have f wedge star f, and you want to turn that into something like a wedge d star f. So you integrate by parts to do that. Then what you get from that process will define your differential of your L infinity algebra. So it won't just be d, it'll be something like d star d.
Yeah.
Okay. And that's it. It's as simple as that. Okay, so any more questions before I go on to applications? So let's come back to this minimal model theorem and homotopy transfer. So the claim was that I've made two claims. One, that any theory, any BV quantizable perturbative quantum field theory corresponds to an L infinity algebra. Let's call the graded vector space V theory. It comes with some brackets. So brackets essentially encode the interactions in the theory. And the claim is that this is quasi-isomorphic to its minimal model, or really an L infinity isomorphism class of minimal models. I'll say something about that later too. Where we have the cohomology of the original underlying graded vector space. And we can get from here to here using the deformation retract of just the complexes, so just thinking of these as complexes for the moment, and then running the homological perturbation limit. But I just want to pause to think about what the data of this complex means in physical terms. So the cohomology here, this is the thing satisfying mu1 of, let's say for a field phi equals 0. Mu1 is the kinetic term in your Lagrangian. These are just the on-shell free equations of motion. This cohomology is really just the physical states of the theory when you turn off all of the interactions. From a particle physicist's point of view, this is the ingoing particles that come into your detector because they're widely spread apart. The interactions are effectively 0. They're just free propagating particles. Okay. So you can take this, now obviously you can embed these free states into the space of the full fields. So this is this E. And you can also project from the full space of off-shell fields onto the physical states. And from the, if you're used to thinking about action formulations for quantum field theories, something that is very intuitive is that the physical states are unique. They're like the physical data of your theory. But your off-shell representation is arbitrary. There are many ways you can embed this in, but there's only one way to project down, and that's the physical understanding of why this contracting homotopy, is doing something there. This contracting homotopy is only the inverse of the differential up to this difference here. So if I project and then embed, that's not necessarily the identity. That's the physical interpretation, is that there are many off-shell realizations of your on-shell physical data. And if you're a quantum field theorist, you should realize from this that this means that H is morally equivalent to what we'd normally call the propagator in QFT. So that was just at the level of the complex. We want to perturb this, and to do that we use the homological perturbation lemma. And this yields the higher brackets of the minimal model in terms of a Feynman diagram expansion of the original brackets. So what's going on here? This is my minimal model 3 bracket, which tells me how 3 particles interact. On-shell physical particles interact to produce some 4th particle. So these are in the cohomology. We embed them in the full space of fields. We act with the full bracket of the full space, and then we project back onto the cohomology to land up with a physical particle out at the other end. And if you look at what's going on here, we just have this diagram. So we really just have this Feynman diagram interpretation. These are the same thing. And from this point of view, this was for the minimal brackets, and we add in the cyclic structure, and that really gives us the amplitude. So a quantum amplitude at tree level, so really that's classical still, for n particles to collide and, well, let's say it's n-1 to collide and produce a final particle, is just given by the cyclic, by dotting in with the cyclic structure of the final particle of the bracket of all of the incoming particles. And then the BV action is quasi-isomorphic to the minimal model action, which we understand, as Martin said, as the generating functional of the S matrix. And as Martin also emphasized, what we see is that actions and amplitudes are really unified as quasi-isomorphic L-infinity algebras. This, the scattering amplitudes that one measures in laboratories are really just the minimal model of these full BV theories. And it's interesting because there is this kind of parallel and quite dominant perspective in particle physics at the moment that you should really focus on shell data only and try to extract everything from the on-shell data. And the message here is kind of, well, these are all the same thing. They're just different. We're just talking about quasi-isomorphic objects. Okay. Oh, why is that there again? A reminder. Okay, so once we've set this kind of general framework up, we can go explore more interesting facets of particle scattering, not just the amplitudes themselves. And I'm going to talk about generalized scattering amplitudes, Witten diagrams, but I'm going to start with color kinematics duality and the double copy. I'm feeling a little self-conscious because I've told this story so many times. I feel like there's a subset of you that may have heard this before, but or definitely have heard this before. Okay, so what is color kinematics duality? I want to write schematically what a scattering amplitude. So here I'm leaving behind the L-infinity algebra picture and just writing this as a quantum field theorist would, a particle physicist would. The amplitudes for gluons to scatter schematically, we can think of this as a sum over purely cubic diagrams with some symmetry factor, some loop integration for any loop momenta running around loops. And then I've got like an integrand, and I want to focus on the integrand. So the integrand has 3 pieces. It's got what's called a color numerator. It's called a color numerator because it's built purely out of the structure constants of the corresponding gauge Lie algebra, the color algebra of the theory. So for QCD, this would be SU3. There are some kinematic numerators, which are built entirely out of the kinematic data carried by the gluons. This is their momentum and their polarizations. And then we've got the propagators, which kind of go along for the ride. These are just the squares of the sums of the 4 momenta on the internal lines of the Feynman diagrams. The color factors are unique. They're just given by the topology of the corresponding Feynman diagram in the homological perturbation lemma formulation of homotopy transfer to the minimal model. So they're just fixed by topology of the graph, whereas the kinematic numerators are non-unique. There are many different ways of writing the same kinematic numerators that give you the same physical amplitude. Now, Bernd, Carrasco, and Johansson conjectured in 2008 that whenever a triple of the color numerators satisfy this identity, Ci plus Cj plus Ck equals 0, which they do all the time, it's just the Jacobi identity. So you'll find the Jacobi identity all over the place. Then these kinematic numerators, there's an organization of them, there's a choice for them such that they will satisfy the same identity. So this is not handed to you. In fact, it will typically fail, but you can find, but remember these are non-unique, you can find a version of them that keeps the physics the same such that they seem to satisfy the corresponding Jacobi identities. Okay, so this is proven at tree level in an array of techniques. One of the more recent ones is by Michael Reiterer, and I'll tell you about this a little because it's really a homotopy algebraic proof of this statement. And it's conjectured to hold at loop level with highly non-trivial examples. In fact, it's known to hold at loop level for certain theories. I'll come discuss this. I'll come to discuss this at some point. Okay, so let me give you some more of an idea of what this really looks like. So this is for 4 gluons to scatter at tree level. So you should think of these as being the kind of diagrams you generate from the HPL. So I've got 2 incoming gluons and 2 outgoing gluons, or if you prefer, you can think of it as 4 outgoing gluons. And these are the Feynman diagrams or the HPL diagrams that you can construct for Yang-Mills theory. And each of them comes with a color factor and a kinematic factor, and I've kind of indicated what they are. So here you just read off the structure constants of the Lie algebra, whatever that is, go into these red bits, and the left is something that I'm leaving unspecified. Here's an example. There we go. I'm only going to go backwards and forwards with this now, I think. So you can see some example here. It's, some momentum and polarization tensors that tell you how the gluons are traveling. We don't just have cubic diagrams, which ruins the statement I said before. I said it was a sum of a purely cubic diagrams. I've got this diagram here that's got a quartic vertex. But you'll notice the structure, I've got the same Cu, Ct, and Cs as appearing here. So you might imagine I can absorb this into these guys, and indeed you can. So what one does is you just divide and times by these Mandelstam variables, which are just the squares of sums with momenta on the internal line. So I times and divide, and then you see I can put this bit, gather again with the 3-point diagrams, the S, T, and U channels in this way. Okay, so I absorb this 4-point diagram into the 3-point diagrams to get this new representation of the amplitude. And this is what I meant by these kinematic numerators not being unique. I've now modified them, right? So they're now a different object. We have the Jacobi identity for the color numerators. That's obvious. What's less obvious is that you now have the same identity for these new kinematic numerators. So you had to do this operation of absorbing the 4-point contact term, and then this just comes out of the box. You could add in one more gluon, and then this whole process becomes much more difficult. There are 15 Feynman diagrams, cubic diagrams to consider. There are 9 Jacobi identities. You have to get them all to be satisfied simultaneously. This is typically just a very difficult problem. People have worked out how to do this at tree level. But what this is saying is that the kinematics appears to be playing by the same rules as the color. It feels like there should be some kinematic Lie algebra associated to this.
Sorry, is this true in any dimension, or is it for
Any dimension.
any dimension? Positive.
Yeah, any positive dimension. Any positive integer dimension. You can do dimensional regularization. It plays nice with this, so we can go to non-integer dimensions if you want. Okay, so why am I interested in this? Okay, that seems cute. It's kind of fascinating. Do you get anything from it? This is the bit where I advertise you do get something from it. So let's look at the gluon 3-point vertex. It's this nice simple thing. This is what I use to construct this. I mean, you could think of this as like as the concatenation of two brackets from the L infinity algebra. It's some relatively simple thing. If I went to gravity, the analogous thing is this. So you can see it's a mess. If you actually wanted to compute with it, this is just 2 of these go into that 4-point calculation I did. 2 of these would go into the analogous gluon graviton 4-point calculation. You can see it would get difficult. Yet, once you glue in the external states, there's this miraculous simplification, and you find that the amplitude for 3 gravitons to scatter off of each other is this simple thing, and it's the literal square of the amplitude for 3 gluons to scatter off of each other. And that made people think, physicists proof by induction, one example holds, all examples that this might just be true generically, that there'll be some sense in which you can get graviton amplitudes by squaring gluon amplitudes. It's a little more subtle, but it's true. So what you have to do is you have to take your gluon amplitude and you have to write them in a form such that these kinematic numerators obey the Jacobi identities that the color numerators obey. You can do that at tree level at least. And then all you do is you take the color numerator and you replace it with a kinematic numerator and you get the amplitude for the gravitons. So given your gluon amplitudes, you get the graviton amplitudes for free. It seems to be an efficient way of calculating scattering amplitudes in gravity. Okay, now, what have I been discussing? All of this is about some hidden constraints, some hidden identities buried deep in the scattering amplitudes. And my whole modus operandi here was to take any constraints or relations and resolve them into some more general homotopy structure. So that's the first thing we should do. Lesson 0 is lift color kinematics duality to a property of the full L-infinity algebra. That's what the instinct should be at this stage, if I've done my job correctly. Okay, so here's a statement. If we assume that color kinematics duality holds at tree level, there exists a quasi-isomorphic L-infinity algebra with new higher products that manifest color kinematics duality. Because it's quasi-isomorphic, it's physically equivalent to the original L-infinity algebra. All of the scattering amplitudes you compute are the same. You get the same numbers for predictions in experiments, but these new brackets manifest color kinematics duality out of the box. How does this work? Well, we kind of just introduce, I mean, the first thing that's done is you introduce new vertices. So you introduce new brackets. The first class of these brackets are what we call the TW or Tolotti-Weinzierl brackets, because they were the people who derived them in all generality. And you just add them. So this would be the cubic interaction for Yang-Mills. This would be the quartic interaction for Yang-Mills. This is like some kind of quintic interaction that enforces color kinematics duality at 5 points, at 6 points, and this tower goes on forever and ever. They don't change the physics because they're identically 0. So that's how you get away with adding these brackets. You're adding 0, but it's a special 0 that decomposes into several pieces, and those pieces correct for color kinematics duality. And I'll come to this later. When you color strip, you get non-zero brackets. So the brackets are non-zero once you've factored out the Lie algebra, the color Lie algebra. The next thing that you need to do is realize color kinematics duality for the on-shell longitudinal gluons and ghosts. Right, the longitudinal gluons don't appear in the scattering amplitudes. They're unphysical. They're not in the cohomology. They're exact. And we have these corresponding ghost fields, and they also don't appear in the scattering amplitudes. But because we want to lift this to the full non-physical L-infinity algebra, we have to think about color kinematics duality for those too. And really what we're doing here is we're perturbing the deformation retract because we're changing our gauge choice. And then finally, we want to lift this all to off-shell fields. So roughly speaking, we'll have some kind of on-shell equation. We'll have some kind of linearized equation of motion, something like box phi equals 0, and we want to lift that condition. This one is problematic. I'll mention why this is problematic in general. Okay, so the logical conclusion to this story is that you can realize color kinematics duality in terms of an infinite dimensional, potentially anonymous. Did I say anonymous? Yeah, that's your fault. Anomalous symmetry of the BV action. So what we're doing is, and I should mention this. I mentioned this strictification theorem. If you have an L-infinity algebra with an infinite tower of brackets, like we'll have generated through this process, here you can always strictify so that you only have a 1 bracket and a 2 bracket. And that's what I have here. This is my 1 bracket, and then my 2 bracket is combining these two, and these are the structure constants of this 2 bracket. The price you pay is generically an infinite tower of auxiliary fields, so unphysical fields that don't, they're not particles that we see in our accelerators. They're just a device to make this happen. And having done that, you realize you can write your action in this form that makes color kinematics duality manifest. So the red Fs are just the Lie algebra structure constants. I've got some metric on the Lie algebra here. We have these the Jacobi identity and the fact that the metric is invariant. And then these blue objects are like the kinematic part of the structure constants. And they obey exactly the same identities. And this really puts color and kinematics on exactly the same footing. Okay. So that's good. We see that color kinematics duality is a symmetry of the gauge fixed BV action. And these Fijks are structure constants of some kinematic Lie algebra. And if we were to integrate out the auxiliary fields, we just get a homotopy relaxation of the Jacobi identity satisfied by these. So when you integrate out the auxiliary fields, you'll just land up relaxing the Jacobi identity up to homotopies in exactly the way you'd imagine. Okay. And what we get from this is loop integrams from Feynman rules that are color kinematic dual. What that means is that in principle, we've proven color kinematics duality to all orders in tree diagrams, in the number of particles you have, as well as loops. Except for there may be an anomaly due to the Jacobian that we introduced when we did this final maneuver here. So potentially something went wrong here, and we introduced the Jacobian when we did that field redefinition, the corresponding field redefinition, that could spoil color kinematics duality. This would be like saying, I mean, what's really going on here is if you want to manifest unitarity at the same time as color kinematics duality, you may have to give up color kinematics duality at the loop level. But we have seen no examples of this. But we do know that it should happen because you could just do a brute force. Well, we didn't, but Byrne and colleagues did a brute force calculation for two loop Yang-Mills. And from that calculation, we know it's not possible to not have some problems of this kind appear for pure Yang-Mill. Okay. And then this double copy, the fact that we get gravity from the double copy of gauge theory also becomes incredibly transparent. We start with our gauge theory action written in this way, and we do this maneuver of just changing everything red, making it something blue. So we just swap all of the kinematic, all of the color for kinematics. And out comes Einstein-Hilbert gravity coupled to an axion and dilaton, and we ride off in the sunset victorious. We've shown that perturbative quantum gravity plus an axion and dilaton is the double copy of Yang-Mills theory, except for the counter terms that are required for unitarity. So you'll generate this theory of gravity. You'll find that you need to add generically, you may need to add counter terms to enforce unitarity. Okay, so that seems all right. I'm happy. There are some downsides. The proof is constructive. You know, we work effectively inductively and say, you know, if we've constructed the vertices that manifest color kinematics duality to order n, we can build the next one. So we don't really have a theoretical, at this stage, we don't have a theoretical understanding or control of the higher vertices that enter into our L-infinity algebra that manifest color kinematics duality. There's no closed form of the color kinematics duality manifesting action for the same reason. It doesn't tell us what this kinematic Lie algebra is. It's something, right? We can't say what it is because we just don't know what these Fs look like generically. You may need counter terms for unitarity, as I already mentioned. And this double copy, while it was simple, it's not obvious what it means mathematically. You want it to be some kind of tensor product of co-chain complexes or something like this, but there's no precise articulation. We did this maneuver. So what we'd like is a clear mathematical characterization of the higher vertices, some closed form for color kinematics duality manifesting action, an understanding of the kinematic Lie algebra. We'd really like manifest unitarity if at all possible so that we get perfect all loop color kinematics duality. And we want some kind of tensor product of C infinity algebras that generates the double copy. But this on its own cannot be correct because C infinity, tensor C infinity gives you back C infinity. We need to get L infinity because its theories correspond to L infinity algebras. So something else has to happen here in this tensor product. Okay. To get going in this direction, I want to mention a very nice result by Michael Reiterer. What he did was to show that color kinematics duality of physical, four-dimensional, Yang-Mills tree-level S matrix, so none of the ghosts or longitudinal modes I've been discussing, really just the physical amplitudes. Color kinematics duality in that case is equivalent to what he called a BV box infinity algebra, which if you're familiar with BV infinity algebras, it's some kind of deformation of that. And I'll show you in a moment what the deformation looks like. And seeing this result, we realized that this would be the right way to lift color kinematics duality off Chow. And indeed, we had already kind of done the work that the kinematic Lie algebra on a BV theory is equivalent to a BV box algebra structure on the color stripped part of the L infinity algebra. So in all of the cases we're interested in, because we're interested in gauge theories, the L infinity algebra is going to be some tensor product between an L infinity algebra and a C infinity algebra. This is kind of kinematics morally. This is color morally. Here it's just a Lie algebra. It's equivalent to this C infinity algebra carrying much more structure. It carries the structure of this BV box infinity algebra. And you can extract what the products, the higher products of this BV box infinity algebra are from the various types of higher products that we produced kind of inductively. So you can see that there are different classes of brackets that are indexed by these I, J, Ks here, and they correspond, roughly speaking, to gauge fixing, Pelotti-Wien seal, and off-shell. And then you realize that the homotopy-Jacobi relations correspond to color kinematics duality on the nose. Okay. So to really see what this structure is encoding, we then strictify or rectify down to a purely cubic theory. This was taking all of the higher products and reducing them just down to the unary and binary bracket. And then we can say what a strict BV box algebra is. So it's a differential graded commutative algebra equipped with a degree minus one differential B. So B squares to 0, such that the anti-commutator with the differential sitting here gives us something that you should think of as being in the center. This physically, this will correspond to the Dell inversion in typical examples. So we need this structure here. And then we insist that B is second order with respect to the product in this algebra. What do I mean by that? I mean that if it doesn't obey the Leibniz rule, it's not a derivation, but its failure to be a derivation gives you a derived bracket, and this derived bracket gives you a shifted Lie bracket. And this will be the kinematic Lie algebra. I'm sweeping some details under the carpet here, but this is morally the right way to think about things. Okay, so let's give an example. We know for other reasons that Chern-Simons theory has perfect off-shell CK duality. So there must be some BV box algebra associated to it. So you could just independently show that Chern-Simons has perfect color kinematics duality. So it holds to all loops. Therefore, there must be some BV box algebra. Just to remind you what Chern-Simons looks like as an L infinity algebra, we've just got P forms valued in some Lie algebra. Here's the BV action that you get out running the handle that Martin described, turning the handle that Martin described. We color stripped to extract the C infinity algebra, which is just a differential graded commutative algebra in this case, strict algebra, because we only have cubic terms appearing in the action. And then we see that the obvious thing, the obvious candidate for B, i.e. the adjoint to the exterior derivative, is the right thing to do. So it does all of the things we want it to do. It's second order, it anti-commutes to produce the Laplacian, and that's what we were after. So it really couldn't be simpler in that case. It's a very neat example. It's a little boring. Chern-Simons being topological has no scattering amplitude. So we've proved all loop order color kinematics duality for a theory that has no scattering amplitude. You win some, you lose some. But it does give us a handle on what the kinematic Lie algebra is. It's given by this derived bracket, as I mentioned. And it just turns out to be the Gerstenhaber algebra on antisymmetric tensor field. Very natural thing for it to be. And if you restrict to just fields, as opposed to ghost fields, anti-fields, and anti-ghosts, you get it's the diffeomorphism algebra of the underlying manifold. Okay, that makes sense. That feels like it's on the right track. And we realize because this gray box is in fact the Laplacian, we really have color kinematics duality on the nose. Okay, so this leads us to a lesson 1. Look for Chern-Simons type actions, right? Chern-Simons has color kinematics duality baked into it. Try to write other theories in a Chern-Simons form. We're all very good at that, so let's go ahead and do it. Definitely not going to get to the other parts of the story. Sorry, man. So the first case is twistorial versions of Yang-Mills. So you could take self-dual super Yang-Mills is equivalent to holomorphic Chern-Simons theory on twistor space. This is something that Martin discussed. And then we have a BV action and a BV box algebra. It's relatively simple to identify what the differential and the corresponding degree -1 operator are. And indeed, the anti-commute to give you the 4D Laplacian. So again, we've proved color kinematics duality to all loop orders. Again, the problem is here is that there are no amplitudes except for the one loop amplitude. And in that case, even that goes wrong. I'll tell you why in a moment. So, but what's going on here? What's happening in this picture? But how are we doing this in such a nice, I mean, this is a very nice, simple action. You can do a kind of Kaluza-Klein expansion on the CP1 of the twistor space. And that gives you an infinite tower of fields. And this is this infinite tower of fields I was describing earlier, right? I said when we strictify all of the brackets we generate by enforcing color kinematics duality, we produce an infinite tower of fields. We've packaged them up into a Kaluza-Klein expansion over twistor space. What's happening here? So that's lesson 2. Look for auxiliary spaces. This is very much like you can encode supersymmetry by formulating your theory over a supermanifold. So pressing ahead, following others, we've shown that super Yang-Mills theory is equivalent to holomorphic Chern-Simons theory on the CR ambi twistor space, and we have a degree -1 operator that anti-commutes to give you this box. This is what it looks like. You can see here, I'm not just getting the Laplacian in this case, I'm getting some extra terms. So we get a kinematic Lie algebra because a BV box algebra gives you a kinematic Lie algebra, but we don't get color kinematics duality on the nose. At least it's not obvious. And the reason is that this box isn't just the 1 over the squares of the momenta that need to run around in these diagrams to interpret it in terms of color kinematics duality. We get all of these terms. If for some reason you've ever tried to do Yang-Mills theory in R-linear gauges away from Feynman gauge, you'll recognize this kind of an issue. And what happens there is that all of these higher order terms just drop out due to Ward identities. And you might hope that the same thing happens here. Turns out that that's quite hard to show, to the point at which I think we've paused on even trying. But we'll come back to that at some stage. But if you could show that, then you'd have all loop color kinematics duality for Yang-Mills, and it would be the first proof of this. So there's like one step left. There's a wrinkle. This can only work for the supersymmetric case because there is a twistorial anomaly for pure Yang-Mills. Going back to the South-Dual Yang-Mills theory, that meant that you needed supersymmetry there as well to avoid this twistorial anomaly. And once you have supersymmetry for the South-Dual case, there are no amplitudes. So in all of the cases where we've proved color kinematics duality holds, there are no amplitudes for it to be checked on. But we can discover new things from this point of view. So there are other kinds of theories out there. One interesting class of theories from the point of view, say, if you're interested in M theory, is consider M2 branes. So M2 branes have a world volume theory, that's the theory that lives on the world volume. So particles have world line theories, strings have world sheet theories, and M2 branes have world volume theories. And because the world volume is 3-dimensional, it looks something like Chern-Simons theory. So you might hope that there would be color kinematics duality. Now it has amplitudes, it has propagating degrees of freedom. And it was shown that they have a 3 Lie algebra, not to be confused with a 3-term L infinity algebra. And this was checked to low orders of points. To check to have color kinematics duality to low orders of points. So you might think it really has color kinematics duality. It looks a little like Chern-Simons theory, and there are some examples. You can write the M2 brane theory in a pure spinor form. You should think of this as the pure spinors. You should just think of it in the same sense as twistor space was kind of an auxiliary space to write this theory. Pure spinor space is an auxiliary space to write this theory. And it comes out looking a little like a Chern-Simons theory. You've got a Chern-Simons like term here, some matter couplings here. And indeed, you can show that this all corresponds to a BV box algebra, and this part here corresponds to a BV box module, so including some matter fields. And this gives you a nice proof that at least at tree level, the M2 branes have color kinematics duality. And this is the first proof of this statement. And it's a proof that was really done through the theory of homotopy algebra, which I think is quite nice.
What do you mean by a 3-Lie algebra if it's not infinity algebra?
Good question. I couldn't tell you the definition right now. So it's got a 3 bracket. It was invented by Bagger, Lambert, and Gustafsson in 2006. Turns out it's essentially equivalent to SU2 cross SU2. It's the only non-trivial example. So it's a reformulation of a standard Lie algebra in terms of a 3 bracket. It had this name for a while, and it kind of eventually got a little muddled, but they're just different things. There was some excitement around them because it seemed like they would be the right structures for describing the theory of M2 branes, but it turns out it only worked for 2 M2 branes. Yeah.
Yeah, but in that case, they are assuming that this is in the conformal fixed points. And they were trying to prove the Magazona conjunction. And then it's true that with Bagger-Lambert, they only could prove for 2 M2 branes. And then later on was relaxed to ABJM.
Yes, yes. So ABJM is the
Or
more
ABJ,
rich. Yeah.
yeah.
But there you lose this 3 Lie algebra structure, and you land up with a traditional color Lie algebra in that case. Yeah. With two SUN factors, where the n is the number of the branes, roughly speaking. Okay. What am I doing for time? I could say a few more things. So okay, so this has all been about amplitudes, which are the kind of most tested observables for quantum field theory. They're the things we tested at the LHC, but there are other things that you might observe, other things you could possibly measure. This is not everything. And we started thinking about how you would characterize these kind of objects in this kind of a language. So things that are not just scattering amplitudes. And the next closest thing are what are called generalized scattering amplitudes. So I have 2 slides on this. So it turns out that the scattering amplitudes that we know and love are not the only asymptotic observables that one can measure. When I say asymptotic, you should think that you've let the particles go to past infinity and future infinity, so they're really widely spread and not interacting. Something happens when they meet. But there are other asymptotic observables that go by the name of generalized or out of time order scattering amplitudes. And these encode various measurable observables of interest, especially for black hole scattering or for Hawking radiation. Where you don't have, it's not like you scatter the radiation into a black hole and watch it come out. You don't do a scattering experiment. You gather all of the radiation from the black hole. And that requires a different type of observable. Turns out from the L-infinity algebra point of view that these are rarely just the same as the standard S-matrix scattering amplitudes in the sense in which Martin alluded to, that there is some kind of a span L-infinity algebra, and you can, and in this case, it's just the L-infinity algebra of the original field theory, but multiple copies of it. And these multiple copies represent going backwards and forwards in time, if you're familiar with the Kaldis-Schwinger construction for quantum field theory. So this guy sitting here, this mother L-infinity algebra, is really just repetitions of the original L-infinity algebra for each time you go backwards and forwards in time. In some, okay, I won't get into that. It's too much to explain. But the point is that you can take the minimal model to the generalized scattering amplitudes, or the minimal model to the conventional scattering amplitudes, and you realize that these are all just quasi-isomorphic instances of the same thing. And this just hammers home that the minimal model is only unique up to L-infinity isomorphism. And these are really just related through homotopy transfer in this way. Let me try say something about holography in the last 5 minutes, and then I'll stop. So all of this leads us, okay. These were amplitudes you might ask about less asymptotic type observables. We're not going to get there, but trying to develop this theme further. And one place to look is in holography. And this was motivated by some questions. So the minimal model has a vanishing differential. And the differential encodes what's called the trivial part of the S matrix. This is the amplitude for a particle to just propagate back into a particle, the same particle, not interacting with anything. And we wondered, given that the differential is absent, where is it in the minimum model? Where is the trivial part of the S matrix? It's gone missing. And one response would be, well, we don't care. That's the uninteresting bit of the scattering amplitude. However, if you go on a non-trivial background space-time, it becomes interesting. And in particular, you might want to consider Witten diagrams, and then it's absolutely essential. And what about non-asymptotic observables? What if you're not going to go to the asymptotic future and past? What if you want to measure something here and then measure something a moment later here and some kind of open subset of space-time? And the intuition is that you should homotopy transfer to a boundary, the boundary being where you make the measurement. That's the kind of intuition here. Okay, so thinking about these things, we came across this very nice paper that had a very nice idea that you should think of holography as homotopy. Cyclicity of the L-infinity algebra generically fails when the manifold has boundary, precisely because of this point that you need to integrate by parts to put things in the homotopy Marraketan form. And to get around this, what you can do is you can add extra pieces to the underlying graded vector space that correspond to boundary fields. So here are some, this is for like a scalar field theory. Here is functions on the boundary, and it's in the anti-field slot. So I'm talking about a scalar field theory. There's no gauge symmetries. This is my physical scalar field. This is its anti-field. And here is an anti-field corresponding to the boundary. And then you modify the cyclic structure in such a way that you recover the correct action, even though you have boundary. And if anyone's familiar with the Gibbons, Hawking, York boundary term from general relativity, this is just like a baby example of that. Okay, so once you've set that up, you can then interpret holography or at least the gravitational side of the ADS-CFT correspondence as being homotopy transfer of the bulk theory to the boundary. And this is quite nice. The deformation retract data gets reinterpreted as a boundary to bulk propagator and a bulk to bulk propagator. And you recover, well, they recover the standard CFT correlators on the boundary that you'd expect from the ADS-CFT correspondence, with the one caveat that to do this, you've got a homotopy transfer to a non-minimal model. The way that this has been adjusted here means that the correct answer sits in some kind of intermediate model in between the full L-infinity algebra and the minimal model. And the minimal model in many cases will actually be trivial. And this is somehow telling, I think this is indicating that the physics encoded in this system isn't invariant under quasi-isomorphisms, which, given that we have said quasi-isomorphisms should be our physical equivalences, this is somehow suspicious and there's something wrong. You could do further homotopy transfer until this theory is completely empty, which doesn't seem right. Anyway, it's definitely in the right spirit of things. There's an idea here. And we thought, how could we fix this? So we had these two goals. How do we incorporate the identity component of the S matrix? And how do we construct corresponding generalized amplitudes such as Witten diagrams as minimal models? I see I'm out of time. So I will tell you the answer is relative L-infinity algebras, where you've got a bulk L-infinity algebra, the thing you know and love, a boundary L-infinity algebra, and a morphism between them. And then the amplitudes are encoded in the relative L-infinity algebra minimal model that still runs through the homological perturbation limit. And you do this thing of transferring to the boundary, essentially. And from this, one can construct the CFT correlators. What you find is you have bulk-to-bulk propagators, which are contracting homotopies. You've got bulk-to-boundary propagators, which are the embeddings and projections. And now a new thing is boundary-to-boundary propagators, which are provided by this L-infinity algebra morphism that takes you from the bulk to the boundary. And you can recover Witten diagrams using exactly the same technology as we had before. very optimistic. Okay, so the future work, color kinematics duality is very special. But in fact, every theory has a homotopy kinematic Lie algebra. This follows from the causal hierarchy. So you might wonder if there's a more general notion of the double copy. I mean, this color kinematics duality is about very special theories. But every theory has a kinematic Lie algebra associated to it. If you like, you can think about this when you color strip away the Lie algebra or the gauge L infinity algebra, you're left with a C infinity algebra that's causal dual to an L infinity algebra. That's your kinematic Lie algebra for your arbitrary theory. What does it mean? Does it mean something physically? This is I'm building on Martin's answer to your question. Integral models. Because you have these boundaries, you should be using these relative L infinity algebras to do the homotopy transfer here. So we're hoping to develop quasi-isomorphisms between semi-holomorphic Chern-Simons theory and integrable models in lower dimensions. Hopelessly ambitious is the other side of the ADS CFT correspondence. We've got some ideas there, but I dare not say them in public. They could be embarrassingly wrong. And had I told you, I mean, if I hadn't just skipped through everything else, the last point would be that you can go beyond the perturbative regime. And you could talk to Friedrich about this. There's a nice construction with AKSZ models as sandwiches where they have two boundary conditions. And by changing the topological boundary condition, you can witness the higher form symmetries for Yang-Mills theory and indeed for gravity in this way. Okay, but I can't tell you about that today. Thank you.